You know, students, I'm going to be honest. I just don't feel satisfied.
He will never be satisfied. I will never be satisfied.
All right, great question. Will I ever be satisfied? Let's see if we can answer that question now. So here is the Jake Abernethy satisfaction formula. You first have to check if I'm nourished, and being nourished means that either I ate breakfast or I didn't go running. Did I exercise? I either went running or walked to work. Was I on time? Either that means I didn't walk to work or I didn't sleep late. And do I feel awake? Well, did I sleep late or did I sleep well? As long as one of those things is true, then I feel awake. Do I have a cramp? Well, having a cramp means either I didn't eat breakfast or I didn't go running. Whether I'm satisfied on a given day is basically just checking if all 5 of these variables are true. And of course, I can then just return that. Okay, so how do I represent my status on any given day? To represent my status on any given day, I just have to fill in all of these variables. Did I eat breakfast? Did I walk to work? Did I sleep well? Did I sleep late? And did I go running? Right? Let's check. Am I satisfied today, given this status? The answer is false. The answer is false. With those variables as set as they are, I'm not satisfied according to this formula. Let's see if we can find another setting of this thing. What if I change this to eat breakfast is true? Let's say eating breakfast, I could change this variable eating breakfast and check. Oh, still false. Okay, how about slept late? Let's make this one true. Still false. Okay, let's try this one. I ate breakfast, I walked to work, slept well, didn't sleep late, and didn't go running. And this one, I'm satisfied. Check satisfaction. I got the answer true. Cool. Now I know how to be satisfied. So this class of problems where you're trying to check if a certain Boolean formula can be satisfied by filling in some input variables. This we call a SAT problem. It's a very famous class of problems, SAT. And typically what you assume is that you're given this Boolean formula in what's called conjunctive normal form. A CNF just means that you have a expression where there's a bunch of ors, an xi or xj or xk, and xl or xn or xm, and then you have a sequence of these various terms. Inside of a term is some or of variables or not of some variables, right? You have that negation symbol right there. But you're combining them with a bunch of these and expressions. Remember, this little wedge thing is an and symbol, and this little v thing is an or symbol. So conjunctive normal form means that you have a list of expressions all joined by ands, and within each expression you have an or symbol within the expression. So a Boolean formula described in conjunctive normal form, what we want to know is, can we find some input x which satisfies this expression? Can we find an x such that happy of x is true? Of course, if you give me an x, if you give me a set of variables, it's very easy to check if the formula is satisfied. It's simple to check if you get true as the output. What's much harder is answering the question of, can I find a setting of these variables such that the expression is true? That turns out to be a much more challenging question, and we're going to be studying problems like that in the next several lectures. What we're learning about now is actually known to computer scientists as complexity theory. Perhaps the most famous problem in complexity theory, and it's a problem that hasn't been solved yet, is the P versus NP problem. You'll soon have a better sense of what that means. What is P versus NP? In general, what you answer in complexity theory is you try to understand what problems can be solved efficiently and what problems maybe we can't solve efficiently. Or at the very least, if we can solve some problem X efficiently, does that mean we can solve some problem Y efficiently? What types of questions can we answer in polynomial time, and which types of problems can we not answer in polynomial time? These all fall into the category of complexity theory. We try to classify algorithmic problems into various categories. The 2 most famous categories, perhaps, are P and NP. So NP are the class of algorithmic search problems for which we can check if a solution is correct efficiently. The class P are the class of algorithmic search problems where we can actually find the solution efficiently. Here, efficiently means that the running time is polynomial in the size of the input. It's worth emphasizing that problems that are in P are always in NP, but not necessarily vice versa. We don't actually have a clear understanding of whether these two sets of problems are actually different or not. This is the classical question of, is P equal to NP? Is there a strict separation between this class of problems P and this class of problems NP? Or are they actually the same set? And it's still an open mathematical question. Okay, so let's imagine we have some problem. We're going to call it foo. The problem foo has instances. You can come up with instances of a problem foo. And you can also come up with proposed solutions to an instance of a problem. So let's imagine we're writing some Python code. You can describe an instance of a foo problem with some string or an array or just some data structure. And you can also describe proposed solutions to this problem instance. Okay, imagine we had some code, we wrote some code, and that code checked to see if this proposed solution actually solved the problem, the instance of foo problem given by this problem description. Okay, let's imagine we had some code for that. That's great, but wouldn't it be great, even better, if we could actually take as input some instance of the problem described by this data structure and actually output a proposed solution? That would be awesome if we could actually take the description of the problem and then somehow output a potential solution. Now, of course, if we have this find solution foo algorithm, we can also test it, right? How would you test it? What you would do is you would just basically plug in the problem description. You would output the solution using this find solution foo function, and then of course you could just call the check solution foo on both the problem description and the solution which you just output. Of course, you want this thing to return true. This is just some test code that makes sure that this thing, which is finding solutions, actually works as expected, because we have this this checking function up here. Okay, so this problem foo, this class of problems foo, we say that it's an NP if the following is true. First, this check solutions foo algorithm has to run in polynomial time as a function of the size of problem description, and it also has to work correctly. So you need this thing to work correctly and to run in polynomial time as a function of the number of bits of problem description. We say that foo is in P if not only can we check proposed solutions, but we can actually come up with solutions, right? We can just take in the problem description itself and output solutions. And it was required that this algorithm, whatever this algorithm is, it has to run in polynomial time as a function of the number of bits of this problem description, right? So a problem is in P if somehow we have efficient code that can find solutions, whereas it's in NP if we have an algorithm that's efficient that can at least check potential solutions if a solution's been provided by, let's say, some other algorithm. Let's look back at that SAT problem, right? Satisfying Boolean formulas. To describe an instance of a Boolean satisfaction problem, you simply have to give the Boolean formula that you want to solve, right? Here is essentially a Boolean formula that I was trying to solve. I wanted to check a bunch of ands of these OR expressions, right? So I had a problem in conjunctive normal form, checking to see if I have a solution to the satisfaction problem. Simply means plugging in the values for status, right? These various status variables, plugging them in and checking to see if the formula returns true on that status, on that dict of true-false values. So checking to see if a solution to this problem is correct can be done very efficiently. It just essentially means plugging in and checking this Boolean formula. You'll notice that I didn't provide an algorithm to actually find what a status could be that would return true. We eventually found one, but how did we find one? If you recall, we found one by simply plugging in various values of true and false until we finally found an assignment of these variables that for which check satisfaction returned true. That algorithm, where you simply go through all possible inputs to check to see if you have something that returns true on this formula, that's not an efficient algorithm. That requires a running time that is exponential in the number of bits of the description of the instance of the problem. So we don't actually like that as a proposed solution. That's not a polynomial time algorithm. So the fact that I've shown you that we have code to check that some potential solution is correct, right? To check to see if status is actually satisfies the Boolean formula. But I can't necessarily give you an algorithm that finds that status variable. This means that the SAT problem is in NP, but it may not be in P. Let's look at another classical computer science algorithmic problem called graph coloring. If I give you a graph, I often want to know the answer to the following question. Can I assign colors to every node in the graph? And let's say you can only use at most k colors. In this case, on the left, maybe you can use at most 3 colors. Can I assign colors to every node in this graph such that for every edge in the graph, the nodes attached to this edge are different? So you'll notice that this edge right here has a red and a blue node, and this edge right here has a green and a blue node. Every edge in this graph, you'll notice that the nodes attached to that edge have different colors. Is it possible to do that with, let's say, 3 colors? In this case, yes, it is certainly possible to do that with only 3 colors because we can see this solution. We can check to see if this solution works. Graph coloring is actually a general case of a special problem that people are interested in, which is how many colors do you need to color a map? You can imagine taking a map with countries on it, and you want to assign colors to the countries, but you want to make sure that neighboring countries which share a border don't have the same color, because then it wouldn't be clear, what the border is between the 2 countries. You want to be able to visualize that on the map. And it turns out this is a classic graph coloring problem. You can put a node for every country, and then you can connect 2 nodes with an edge if they share a border. And there was this famous open question, which was how many colors do you need to color a map to ensure that this property is true, that neighboring countries have different colors? And it so happens that the answer is 4. You can always take any map and color it with 4 colors and ensure that no neighboring countries will have the same color. It turns out that graphs that emerge from maps, they're called planar graphs, have a very special property. They're limited in how you can construct these graphs, and it turns out that means that you can be sure that they can be colored with only 4 colors. So I won't go into any more detail about that, but in general, if I give you an arbitrary graph, the question of how many colors you would need to color it with, what was the minimum number of colors you could use to validly color the graph, in an appropriate fashion, right, so that neighbors have different colors, it's actually not clear how to answer that question. So let's ask the following question. Is graph coloring in P? Is it in NP? What do we know about this algorithmic question? So I'm going to claim that the graph coloring problem is indeed in NP. It's in NP. How do we know that it's an NP? Well, it's actually pretty easy to check if you have found a valid graph coloring. So let's say I start with the problem. The problem is some graph, G, and we're given some num colors constraint. You can only use so many colors to color the graph. And here is a potential solution. Let's say coloring is just some dict that defines a color for every vertex. So first I'll just check to see if the number of colors being used in this coloring is not too big. You're just checking to see if the number of unique entries in coloring is appropriately sized. It doesn't go over the num colors constraint. That's fine. And now I'm going to just simply look at every vertex and then at every neighbor of that vertex. Right? This is just running through all of the edges in the graph. And I'm just going to check one thing. Is the coloring for that vertex different than the coloring for the neighbor? I'm just checking if this condition is true. I want the colors of a vertex and its neighbor to be different. And if they're different, I'm just going to append this. I'm going to append this whole thing to this check edges array. And in the end, I return true as long as all of these checks came out true. So I just checked to make sure that this value different was true for every edge. It's so simple. You gave me a graph and a coloring and a maximum number of colors, and I was able to check very easily, did this solution satisfy the constraints that I needed it to satisfy? Is this a legal, valid coloring of this graph? The harder part, of course, is actually finding the coloring. How did I come up with this thing? To be an NP, for a problem to be an NP, I just have to check if solutions are correct. In this case, I checked if the coloring was appropriate and it was legal. But how did I actually find a coloring? Can I come up with some code that looks at a graph and a maximum number of colors and somehow outputs some potential coloring? It actually, checks if finds some coloring, maybe tests if it works, and then returns it. Can I write code like this? And it turns out that, well, I'll let you know that if you could write some code like this that produces an efficient solution that finds graph colorings, you become very famous immediately. And we don't actually think that this is possible. We don't actually have a proof that it's not possible yet. There's still open questions about this. This is the P versus NP problem. But we think it's highly unlikely that you'll be able to find an efficient algorithm that outputs a valid coloring. And by efficient, I mean it has to run in time polynomial in the size of the graph and the description length of the graph, which is basically just the number of vertices plus number of edges. I decided to write some code that might help you on the quiz for this day. You might want to just take a careful look at this code before you go to class. Good luck. Let's just finish with one cool idea that we'll dive into much more over the coming lectures. You can reason about the difficulty of different types of problems by seeing if somehow one can be converted into the other. Imagine, let's say, that you had some class of problems B, some problem type B, but you actually want to solve some problem A, some family of problems of type A. What if problems of type A could just be converted into problems of type B? Well, this would be amazing. You could then do the following trick, which we call a reduction. And we're going to be looking at a number of reductions over the coming days. The approach you could take is simply to take some instance of the problem, let's say of type A, do some conversion, modify x to y, which is now of type B, take whatever algorithm you have for solving instances of B, get the answer back, convert the answer back to an answer of type A, and then output this answer. This trick is used all the time to reason about the relative complexity of various algorithmic problems, and we're going to see several examples of this where we convert problems of one format into problems of another format. We apply some polynomial time reduction to get between these two problems, and then that'll tell us that essentially one problem is strictly more difficult than another problem. I'll explain in more detail what I mean by that in the coming lectures.